Hello everyone. Now let us start with isomerism in coordination compounds. So today we'll discuss about how will you find out the number of stereoisomers like geometric isomers or optical isomers in coordination compounds. And later we'll talk about the structural isomers. So before we proceed for this all this in detail, we just have a look how these isomers can be classified. So isomers, these are of two types. One is stereoisomers and other are structural isomers. These stereoisomers, so the word stereo means the position of the ligands in the space. So that position in the space of the ligands, it will just distinguish them into two different types. One is geometric isomer and other is optical isomer. In case of optical isomerism, you have to aware about the plane polarized light and all. So we'll discuss in detail later on. So basically these stereoisomers, those are of two different types, geometric isomers and optical isomers. So these geometric isomers are also called as distereoisomers and optical isomers are also called as enantiomers. They should not be mirror images of one another. Then structural isomers, those are of four different types: linkage, coordination, ionization, and solvent isomers. So this part of this isomerism, that is stereoisomers, will be just discussing in detail about the geometrical isomerism and optical isomerism. So as I already told that geometrical isomerism means the position of the surrounding ligands to the metal in the space, that is geometrical isomerism. Now the geometrical isomerism in tetrahedral complexes. Here you can see here I wrote here no geometrical isomerism. These tetrahedral complexes, they do not show geometrical isomerism. Now this is why this is so. This is the tetrahedral structure. If you draw this way, this I wrote right with the dotted line, and this is other side of the screen. These are the four ligands attached to this metal atom. Now, if you flip this A and D, so this angle in case of this tetrahedral structure, it is 109 degrees and 28 minutes. Okay. Now, when you flip this A and D, means this A ligand and D ligand, if you flip this, there is no change in the angle. So this angle won't change. And stereochemistry also do not change. So as there is no change, even if you flip the ligands, so the geometrical isomers are not possible in tetrahedral complexes. Now geometrical isomerism is not possible in tetrahedral complexes having two different types of unidentate ligands. Now these ligands, all these ligands which are attached here to this metal, these are unidentate. It means there is only one donor atom. It means. Why this is so? Because the relative positions of unidentate ligand. Unidentate means there is only one donor atom. Unidentate ligand which are attached to central metal atom. Are same with respect to one another. And that is why this geometrical isomerism is not possible in tetrahedral complexes. Now, when I say geometrical isomerism, there are two different types. One is cis and other is trans. You have studied this in organic chemistry. Now, what about the geometrical isomerism? I write in short that GI means geometrical isomerism in square planar complexes. Okay. square planar complexes. Okay. So in case of the square planar complexes, if the complex is of, we'll study one by one different combinations of this metal and ligand, and a four type of complex. Is one metal atom and four unit ended ligand. It means, so you can draw the structure like this, and a four type of ligand. This is the way you can draw the structure of the square planar complex. So if you flip this, means if this A and A, if you flip this, there is no change in the structure because all these ligands which are attached here, those are same. So even on the flipping of the structure, there is no change in the structure. So no geometrical isomerism is possible in square planar complexes of Ma4 type. Remember. Okay. Now, next thing, second, Ma3b means three ligands are of same type and one ligand is of another type. So you can draw the structure for this like this. One, two, there should be three A type of ligands. So I will write here A3B. Another way, I can write for this like this, AA and A here and B here. So I just interchange the position of this. Okay. So here also, if you flip, there is no change in the structure. Remember, even if I change this position, the structure remains the same. So how will you know that whether there is a cis or transform? So when I say that the geometrical isomerism means there should be two different types. One is cis and another is trans. Okay. So cis means the adjacent position of the ligand, and trans means the opposite positions of the ligand. Remember this, you should always remember cis and trans isomers. So how do we find out whether this is geometrical isomerism is there or not? So you just go through this diagonally opposite positions of the ligand. Here diagonally you can see this. This is AB, isn't it? And if you go there, here also the combination is AB, isn't it? Now, even if you flip this structure, no geometrical isomerism is possible. Remember, or you can go in another way also. Means if this is the situation, means if you see diagonally opposite ligands are in this structure and in this structure the same, even this also the same. So in such cases, no geometrical isomerism is possible. Or other way, you can write the combinations. Means for this type of this Ma3b, the possible combination I can write for the ligands like AA diagonally is AA, and then another is AB, isn't it? So another is AB. So this is the one, only one combination is possible. You can't write any other combination out of this. So only one combination is possible there. So no geometrical isomerism in these type of complexes. Remember. Okay. So even without drawing the structure, you might be able to know whether this type of complex will show geometrical isomerism or not. Another, we'll proceed for the next type like this. Third one, Ma2B2. Now remember, in every case, it is a square planar, means only four ligands are there. And the structure is square planar, not tetrahedral. Now the possible combinations for ligands of A2B2 type of complex, that is Ma2, M stands for metal, two A type of ligands and two B type of ligands. Okay. So the possible combinations here we can write number one like AA, okay, and another that is B. Next thing, next combination you can write as AB. Just multiply this first bracket with the second one, AB, and this also AB. Okay. So this is the way, these are the two possible combinations. So by knowing the possible combination, you can know the number of geometric isomerism possible. Now, if you try to draw the structure for this combination and this combination, you can draw this way. Now, if the question is asked like this, how many number of geometric isomerism are possible in Ma2B2 type of complex? So the answer is 2 types. Okay. Now, obviously, one is cis and other must be trans. Now we can draw the structure for number 1 combination. Here AA and BB. Okay. Other, you can draw the structure like this. Rather, this is for the second one. I'm sorry here. Now you can write for this number 1 now. Here, this is AA and BB. So by drawing the structures, these combinations or these pairs of ligands, those are oriented diagonally opposite, remember. Okay. So this, the structure for this second combination is this one. And for this first one, this is the structure. Now which one is cis and which is the trans here? So in this case, these two A, these are on the, these are adjacent to, these are having the adjacent position. So this is your cis and these are the opposite position, this A and A. So this is the trans. So this is cis isomer and this is trans isomer. Now here, in other way you can write this as AB, AB. So this AB, AB and this AB and AB. These are perpendicular to one another. Or in other way you can write here AB, AB. These are perpendicular to one another. And that is why this is the cis isomer. So this will help you to identify cis and trans isomer. Or you can write that it's AA and BB. I'm talking about the ligands. A and BB are on the same side. Are on the same side of square plane. We are talking about the square planar complexes. Okay, so this is cis isomer. So adjacent position means cis isomer. So I can write here adjacent. So that is cis. And in case of this structure, this one, this AA and BB, this AA and BB, AA and BB, which are perpendicular to one another. Perpendicular to one another. Okay, and AB and AB, this AB and AB, two different ligands are on the same side of the square plane, and that is why this is the trans isomer. So how many number of geometric isomers are possible here? In Ma2B2 type of complexes, number of geometric isomers equals to 2. Okay. So even if you don't draw the structure, just by knowing the possible combinations, you can easily come to know how many number of geometric isomers are possible in these type of complexes. Okay, I just explained you just to know which one is cis and which one is trans, because the many MCQs are asked based on this, which is cis and which is trans. So you should understand what is cis isomer and what is trans isomer. Now, Cis means always you remember adjacent positions, same or on the uh, adjacent to one another, and same groups are attached to the other side of the complexes, means perpendicular to one another, that is at the opposite position like this. Okay. Now the next type of complex, the fourth one, we are talking about the square plane, MABCD. So first of all, you just try to find out the possible number of combinations. So there are four different types of ligands, so you can arrange them as AB, other is CD. Next, just solve the brackets. Try to solve the brackets. Multiply this with this. Okay. So AC and BD. This is the second possible combination. And the third you can write like A, D, and B and C. Just you always remember there should be no repetition. This combination should not be repeated. AD, this A and D, and remaining with the B and C. So just cross check. This is a totally different. All these three combinations are different from one another. Therefore, number of geometrical isomerism possible in MABC type of complex, that is equals to 3. So even without drawing the structure, it is possible for you to know the number of geometric isomers. This type of questions are there in different competitive exams like JEE mains or NEET. Next is MA to BC. In this type of complex, the possible combinations you can write 1, 2, and 3. Now the number 1, that is AA and BC. There are 2A, so the 2A and B and C. Now another combination you can write like this: AB is A and B, and another you can write B and not B, A and C. Okay, AC. So just multiply this A to B, this A to C. So this is the way you can write two possible combinations. So there is no third combination possible. So geometrical isomerism possible in this MA to BC type of complex, that is equal to 2. You can draw the structure also if you want, like this. Like this. B and C, A and A. Okay. And other is square plane structure, like B and A. And next is A and C. Isn't it? So when you look at this, which one is cis and which one is trans, as I told that you have to look for the opposite thing. So this is of course the cis one, same on the same side of this, and this is the trans. The same ligands are on the opposite side. Okay. Now the next type we can go. Now this is about the square plane. We were talking about different square planar type of complexes and how to find out the number of geometric isomerism in different square planar type of complexes. Remember. So this is the first one. There is no geometric isomerism possible in tetrahedral complexes. In square planar complex MA4 type, if it is MA4 type, no geometrical isomerism. Even in this MA3B, no geometric isomerism. You have to remember this, all these things. Then MA2B2, possible combinations are 2, so 2 geometric isomers are possible, sorry. And In 4 type, if this is the type of complex where all the 4 ligands attached to this metal ion is different, so 3 geometric isomers are possible. If this is the type of the complex, then 2 geometric isomers are possible. Okay. So this is the easiest way you can find out. If you use this trick, you will be easily able to find out number of geometric isomers in square planar complexes. And remember always, there is no geometric isomerism possible in tetrahedral complex, but there is possibility of having optical isomers or enantiomers in case of tetrahedral complex. Now, remember here, as I told, no geometric isomers are possible in tetrahedral complex and no optical isomers. We'll be discussing this optical isomerism later on. No optical isomers in square, which is very important here for you. Square plane complex or square planar complexes. So this is the simplest way you can be able to find out number of geometric isomers in square plane complexes. In the next video, we'll talk about the geometric isomers, optical isomers in octahedral complexes. Up till now, we did not discuss about the octahedral